The first transport layer protocol we're going to talk about is the User Datagram Protocol, or UDP. Now, I've chosen to start with UDP because it's really the simplest transport protocol. It demonstrates the usage of ports, so we can talk about how ports play into the concept of a stimulus and response. And it doesn't actually embody and embrace all of the concepts of what we've talked about with the transport layer protocol, in that it doesn't actually provide reliability. And that's why I've called it a pass-through service a couple of times, because UDP is used when you need a transport layer protocol and you need the ability to utilize source and destination ports, but maybe you're not as interested in the reliability features that are provided by something like TCP. So the big thing to understand with UDP, again, is it's the most simple transport layer protocol that can be used between the two options here, and it really doesn't have any reliability built in. And it's for that reason UDP, for a lot of people, has come to stand for unreliable darn protocol. And that's just saying that when you send traffic or send packets over UDP or utilizing UDP, there's no built-in guarantee or mechanism to guarantee that they're actually going to get to where you want them to get to. So if you're concerned about that, if you're concerned about packets getting to where you want them to go to, you better hope the application layer protocol in use has some functionality that will make sure that happens. Now, that brings up the question of usage. Well, you would think, doesn't everybody want to make sure their packets get to where they're going? And certainly they do, but think about this, that we're talking in terms of scale. You're talking about, if you drop one packet out of 100,000 packets, is that really going to mess things up? And with a lot of protocols, it might not. So there are a couple of usage scenarios where UDP makes sense. One of those is paired with protocols, like we mentioned, with built-in reliability mechanisms, things that already will provide some level of error detection and recovery. We also have use cases concerned with speed. Since UDP is a simpler protocol, it doesn't have all those reliability features and all that additional overhead. You'll see in a minute the header structure, it's much, much smaller. So UDP can communicate a lot faster, both in terms of network bandwidth being taken up and in terms of processing on the sender and receiver. So if you're really concerned about speed, UDP is generally going to be a little bit faster. The next use case is when you're not concerned with sequence. An important feature of TCP, as we'll see later, is the ability to reassemble packets regardless of what order they're received in. So being able to structure things appropriately and maintain a sense of sequence amongst packets. UDP doesn't have that ability. It has no ability to make sure packets are delivered in sequence. So you might prefer UDP if you're not concerned about that type of sequence. Finally, smaller burst transmissions. So if you're just sending really quick bursts of information periodically, UDP might make sense there. So we'll talk about a few different protocols, application layer protocols that rely upon UDP when we get into that section. Things like DNS or DHCP and why they chose to use UDP. But some of the other places you'll often see UDP are with streaming media. So when you talk about sending video data, streaming video or streaming audio over a link, generally it's not going to matter if you drop 1 out of 100,000 or 1 out of 1,000,000 packets. It's not going to make a big difference in terms of noticeable impact on the user. So that's a common scenario, is that streaming media example. But again, we'll look at a bunch of different examples moving forward. We'll cover UDP here and really every field in the header because there's only a few. But if you want to read a little bit more about UDP, you can do so in RFC 768. You're looking at the UDP header now, and you'll notice it's pretty darn small. It's pretty simple, so it's maybe one of the simplest protocol headers we'll look at, which is, again, one of the reasons I started with UDP before TCP, to kind of ease you into these concepts related to transport layer protocols. Now, we only have 4 fields here. Each of them is a 2-byte field, so we have, in this case, you count those up, 2468. We have an 8-byte header, and that's the standard for UDP packets. Now, the first 2 fields I want to talk about are source port and destination port, and those are simply where we store the port information that I discussed earlier when I described why ports exist, why they work, how we bind services to ports, and so on. So at UDP 0, we have the source port, and UDP 2, we have the destination port on the first row of this graphic here. So when a system transmits data, it chooses a source port, it sends that to a specific host on a destination port, and if that system responds, it will actually flip those values. So the source port will be the transmitter, the destination port will be the recipient, regardless of who's initiated the communication here. So those are those two fields. Pretty straightforward. Notice each one is a 2-byte field. I mentioned earlier the maximum value for a port number is 65,535, and that's because that's the maximum decimal value for a 2-byte field, which is what we have here. A couple other values of interest. At UDP 4, we have the packet length. So you see that on the first field on the second row. And the packet length is another one of the many length measurements we've seen across the protocols we've looked at. But in this case, this is going to be the UDP header size, which is going to be 8 bytes, plus the packet payload size. So that's going to be everything after or embedded within the UDP data. So it's probably going to be, in most cases, generally your application layer data. So if you have a DNS request, it's going to be all that DNS data plus the size of the UDP header, that 8 bytes there. So that's going to be your packet length. Finally, at UDP 6, we have the checksum value, and it's used once again to verify the integrity of the packet, that it hasn't been changed or manipulated as it comes across the wire. While UDP doesn't have any reliability features to the extent of TCP, you could say that checksum is to some degree a reliability feature, but it's not reliable for the data that's contained within the application layer that may be attached to the packet. It's really only concerned about the integrity of the UDP header, and in this case, the IP header. It's actually looking across both of those. I won't get into the mechanism in too much detail here because it doesn't really matter for our purposes, but this checksum field works very similarly to an IP checksum, and that it takes a few specific fields from both the UDP header and in this case the IP header that is along with it, and it chooses those fields, groups them into 16-bit groups, inverts those bits, adds them together, and that's where you get your checksum, which is a 2-byte field. The important thing to note is that when systems are processing a packet and they detect an incorrect checksum, they calculate it themselves and it doesn't match what's included in the packet, they'll silently discard the packet. So it's a way to ensure and protect against corruption of UDP and IP headers in transit, but again, doesn't provide any reliability for the actual data that's being transmitted via the application layer protocol.